That good, huh?
Yeah.
Sounds good. Do you have any questions?
Number 16, part B, on 31. All real units.
As it turns out, it is not. We have g of t is equal to the square root of 1 minus 2 to the t. So what we're looking for is, we're looking for 1 minus 2 to the t to be bigger than or equal to 0, right? So obviously we haven't really learned logarithmic functions or anything like that, but the idea is that 2 to the t has to be less than or equal to 1, right? And if you go on a picture, 2 to the t will have a graph of this nature, where this point has coordinates 0 and 1, which means this line is y equals 1, and so this means that t is less than or equal to 0. And so your domain is just minus infinity to 0. Does that make sense? Okay. What else? Sorry? 26? Bless you. The limit is -1. I don't know if that actually helps. We're looking at the limit as x goes to infinity of 2 plus 10 to the x divided by 3 minus 10 to the x. And the idea is that if we force out a 10 to the x on top and on the bottom, what are we left with? Two times 10 to the minus x plus 1 divided by 3 times 10 to the minus x minus 1. And the idea is that the limit as x goes to infinity of 10 to the negative x is equal to 0. And so this whole thing is just 1 over minus 1, so it's minus 1. Does this make any sense? Yes?
Where do the ones come from?
These ones?
Yeah.
Well, I'm factoring out 10 to the x. So what happens when you take out a 10 to the x? You're left with 1.
Oh, yeah.
It's kind of like the same trick we applied for 25 when I did in class. Factored out e to the 3x. If you remember, Friday. Okay. What else? Okay, so today we're going to start talking about inverse functions, and also we're going to talk about logarithmic functions. So I guess first things first, let's talk about inverse functions. So do you remember what is the definition of a one-to-one function? This was again actually part of your pre-test, right? More or less. We talked about it as far as review was concerned. Do you remember it at all? Should I spend the time talking about it? Okay. So the key idea is excuse me, we need to talk about inverse functions. So the idea is, how can I talk about an inverse function? So in order for me to talk about an inverse function, I have to actually define what a one-to-one function is. So a function f is called a one-to-one function if in words your textbook says if it never takes the same value twice. Let me write it out. If it never takes the same value twice. Or in notation it says that f of x1 is not equal to f of x2 when x1 is not equal to x2. So it basically says given any 2 points, the function is not going to have the same value at those points. Okay? Now graphically speaking, it's actually very easy to interpret when a function is one-to-one, in the sense that if it doesn't have the same value twice, it means that it'll pass something called the horizontal line test. So a function is one-to-one if and only if no horizontal line intersects its graph more than once. Does that make sense? Do you understand why that's the case? Yes?
So sine and cosine can be correct?
No. Sine, cosine, tangent, cotangent, actually all the trigonometric functions are not one-to-one. Which shouldn't surprise us considering they're all periodic functions. So after every 2 pi or pi, depending on which function you're looking at, your function is going to take the same values over and over again. So what we're going to do at the end of the section is actually talk about inverse trigonometric functions, and we're actually going to limit our domains to a piece in which it's actually one-to-one. Okay, does this make sense? Let me see. How about we look at, should I define inverse functions as well and then look at some problems, or you want to just look at some problems of one-to-one functions right now? Should I take a coin and flip it? Look at one-to-one? Okay. So, you have a couple of problems to do for homework. I think it's like 6 and 10 or 6 and 12 or something like that. That is related to one-to-one functions. So let's see. You're supposed to determine whether or not the function is one-to-one. So if I look at number 5 on page 159, the graph looks like this. So is this a one-to-one function? Yes?
Well, you can draw a line to it twice.
How does?
Never mind, horizontal.
Right. So because it passes the horizontal line test, it's one-to-one. Does that make sense? Yes? Okay. How about number 7? Is f of x equal x squared minus 2x 1-to-1? No? Why not?
X squared.
And?
Parabola.
It's a parabola, right? The graph of a quadratic function is always going to be a parabola, right? But how do we show it? Considering our definition tells us that f of x, it tells us that function's one-to-one if it doesn't take the same value twice, right? So to show that it's not one-to-one, how should we approach it?
That's number 9.
That's number 9? Okay, number 9 it is. No, because f of 0 is equal to 0 and f of 2 is also equal to 0. I found two distinct values for which the value of the function is the same. Does that make sense? Yeah? Again, keep in mind the distinction between the actual graph, and when you actually have the graph, when you don't have the graph. At this point, we're actually given this particular function. We may or may not know what the graph of the function looks like, because I could actually look at x to the 4th instead of x squared, for example, and then you wouldn't necessarily know exactly how to graph it, especially if I actually add some other values in it. Does that make sense? Okay. How about 11? G of x equals 1 over x. And again, what we're actually striving for is not the actual graph, because if we know the graph, then it's kind of making our life a little simpler. So how should we show this without actually having a graph? First of all, do we get a hint about this as being one-to-one or not? How about we start off in the following way? Let x1, x2 be distinct. That is, x1 is not equal to x2. Can we show g of x1 is not equal to g of x2? Because if we can, then we show that the function is one-to-one. Does that make sense? Is that making sense or no? Okay. So what is g of x1? 1 over x1. What is g of x2? 1 over x2. Not x squared, but x2. Right? Well, 1 over x1 equals 1 over x2 implies, or is equivalent actually, to x2 being equal to x1. Right? Cross multiply. So since the right hand side is not true, right? So since that actually is not equal to it, then the first one is also not equal to. So we showed g is one-to-one. Does that make sense? Yes? Okay. Well, that's basically the idea behind one-to-one functions. So let's come back and actually talk about inverses now. So, definition. Let f be a one-to-one function with domain capital A and range capital B. Then its inverse function f to the minus 1 has domain B and range capital A, and is given by f inverse of y is equal to x is equivalent to f of x is equal to y. In words, f inverse undoes what f does. So f is an operation, right? You start with x, whatever operation f makes, f inverse does the exact opposite, and so you come back with x. Does this make sense? Yes? Again, you've seen inverse functions before, right? So that's why I'm not necessarily spending a lot of time on it. Now, the one thing I should point out is that, and again, since you've seen them before, I'm hoping nobody's ever going to make this mistake, but not, nonetheless, let me just write it out. F to the minus 1 of x is absolutely not equal to 1 over f of x. Okay? Maybe I should... Okay. All right. So what happens if I take f composed with f inverse of x? What do I get? Anybody has a thought? I get f of f inverse of x, right? And it is equal to x. Similarly, f inverse composed with f of x, which equals f inverse of f of x, is equal again with x. Does this make sense? Yes? Remember what I said in words. Whatever f does, f inverse undoes, right? So if I start off with x, or if I start off with x, I apply f inverse to it. As soon as I apply f to it, I have to revert back to x. Okay? Alright. We're going to try and find inverse functions in a second. What is the geometrical interpretation of f inverse of x? Because of the way these work, if I have a graph of f of x, so this is y equals f of x. Do you remember how the graph of f inverse looks like?
Switch out the range of the domain.
Because we switch out the range in the domain, in reality, what we're doing is, when we're graphing it, we'll get a line that's reflected along the line y equals x. So this is the line y equals x. Does that make sense? Why would that be the case? Well, because what we're doing is we're interchanging x and y. That's basically the bottom line. Okay. So with that in mind, how about we actually look at some functions? Let's see. How about we look at 21 on page 159. F of x equals the square root of 10 minus 3x. You're probably only asked to find the formula for the inverse of the function, but I'm actually going to do a little more than that. I want to see how how you're thinking about things. Can you tell me what the domain and what the range for f are? Let's focus on the domain for now. What would the domain be? Negative infinity to close, 10/3. Right? Everybody sees that? 10 minus 3x has to be bigger than or equal to 0, which means 3x is less than or equal to 10, so x is less than or equal to 10/3. Yeah? Okay, so the goal is to find f inverse of x. So this is usually the standard way of finding inverses. Do you remember how to find inverses?
Yeah.
Step 1. Y equals the square root of 10 minus 3x. Step 2. Interchange x and y. So we have x equals the square root of 10 minus 3y. And step 3, solve for y. Do you remember this? This was pre-calculus. Okay. So what do we get? X squared is equal to 10 minus 3y. Right? So 3y is 10 minus x squared. So y is equal to 10 minus x squared divided by 3. Right?
Could also be negative x squared minus 10 divided by 3.
Y negative. Oh yeah.
Yeah, because I just said
Negative x squared plus 10. Right?
negative x squared plus 3.
Mm-hmm. So f inverse of x then is equal to 10 minus x squared divided by 3. Right? What's wrong with this? Is this a one-to-one function? No. So if it's not a one-to-one function, how can it be the inverse? By the way, I should point out that if you take the inverse of the inverse, you end up with f of x. So how can I take the inverse of this if it's not a one-to-one function? This is where we come back up here and we figure out that the range is 0 to plus infinity. And so when we come down here, x has to be bigger than or equal to 0. Okay? Does this make any sense? As I said, I'm doing a little more than the problem asked because I wanted to give you a little bit of a perspective on how inverses work. Do you understand why that's the case?
How do you know it's not a one-to-one?
Because it's quadratic. So it's going to look like a parabola. Right? Do you understand this? See, if you think about it graphically, y equals the square root of 10 minus 3x looks like do you remember the graph of square root functions? So when x is 10/3 you get 0, right? So I'll start over here, right? And then now when x is 0 I end up with square root of 10, which is a little over 3, so I don't know if I want to give some units. 1, 2, 3. It'll look like that. Right? So now if you think about graphically, if you are to actually flip this over the line y equals x, what would you get? Something like that, right? Does that make sense? Now keep in mind that if I am to actually look at the graph of y equals 10 minus x squared divided by 3, you will end up with the entire parabola, right? But you only have to look at half of it, or we're forced to look at only half of it, because that's just the inverse. Does that make sense? That's why I wanted to ask you what the range was originally. That way we know exactly what we're looking for the domain of our inverse functions. Okay? All right.
Does that work then? Is that the, I mean, if the range is different, you can still do the inverse?
In what sense? The inverse is that. So you have to specify for what values of x you're looking at. Again, the key idea is even though when you work it out you end up with a quadratic, it still has to be one-to-one. Because if it's not, then you can't actually apply the laws and, you know, get back to your f. Okay? All right. So, questions about this?
Okay, this is a little algebra that I might have forgotten, but when you have 10 minus 3y, and you do the inverse methods for solving for y, interchange, I usually just subtract the 10,
Okay.
leave the x negative, but I still got 10 minus x squared, and it's supposed to be negative 10.
Well, you end up with 10 minus x squared?
Yeah, but that's wrong.
That's correct. 10 minus x squared over 3.
Over 3.
Isn't that what I have?
I meant x squared minus 10.
Okay, you get x squared minus 10 equals to negative 3y.
And then you divide by negative 3.
So then you get y equals x squared minus 10 over negative 3,
Yeah.
which is the same thing as 10 minus x squared over 3.
Okay.
Right? Okay. Let's look at a particular theorem, and then we'll come back and talk about logarithmic functions, since we haven't actually talked about that at all. The idea is the following. If f is 1-to-1 and differentiable, and f prime of f inverse of a is not equal to 0, then f inverse prime of a is equal to 1 over f prime of f inverse of a. The key idea behind this is the following. The left-hand side looks relatively ugly, but it doesn't look as ugly as the right-hand side. But what is the left-hand side? It says f inverse prime of a. Okay? Geometrically, what is that actually telling us? It actually asks us for the slope of the tangent line of the inverse function, right? So if I'm to actually look at, let's say I have this function, I have my inverse. If I look at this point, the corresponding point, the question is, what is the tangent of that line? Or the slope of the tangent of that line. And that's basically how they're related. Okay? So, with that in mind, Let's look at problem number 35. It says f of x is equal to x cubed plus x plus 1, and a is equal to 1. We're asked to find f inverse prime of a. And you might ask yourselves, why exactly are we doing all of this? Because it looks quite messy. But the key idea is, if I would be able to invert this function, then all I have to do is come up with f inverse, take the derivative, and apply a to it, right? Problem is, what if I can't find the inverse? Well, I didn't give you the theorem for nothing, right? So the idea is that f inverse prime of 1 is going to be equal to 1 over, do you remember what the theorem says? F prime of f inverse of a. So f prime of f inverse of 1. Yes?
Okay, so when we do solve that out, do we take the inverse of it and then derive, or do we derive first and then take the inverse?
Here,
Yeah, if we could solve it out.
you would have to take the inverse and then take the derivative. But the problem is, it's a cubic. And we don't know how to solve cubic polynomials, right? Does that make sense? If it would be a quadratic function, you would apply the quadratic formula and you would be able to solve it. But because it is not, you don't know what to do. Does that make sense? So how do we approach this problem? Notice what actually the right hand side says. It's f prime of f inverse of 1. Okay? I don't know how to come up with f inverse prime, but I know how to come up with f prime. Okay? So the idea is the following. What is f prime of x? 3x squared plus 1, right? So if I can figure out what f inverse of 1 is, all I have to do is just plug it into n for x, and I get my solution. So now the question is, what is f inverse of 1? Well, remember what inverse functions are. The idea is f inverse of y is equal to x if and only if f of x is equal to y. Right? This means that we need to find x so that x cubed plus x plus 1 is equal to 1. I'm assuming everybody can see what that is?
0.
0. Right? And so f inverse of 1 is in fact equal to 0. Which means f inverse prime of 1 will equal to 1 over f prime of 0, which equals 1 over 1, which equals 1. Is that making any sense? Or is the headache starting to set in? What I would like you to know how to do is to actually apply the theorem. I can never remember exactly what the theorem says. So if I'm giving you a problem like of this nature, I will probably actually give you the formula. But you still need to know how to apply it. And this is basically where this particular problem comes into play. Yes? Which one?
Like the line that says find x so that x cubed plus x plus 1 equals
Color coding. Since they're all ones and zeros. Does that make sense? This is the key idea. F inverse of 1 is equal to x means f of x is equal to 1. Okay? Any other questions?
So let's look at something. Why can't we just take the inverse of x cubed plus x plus 1?
Well, because x cubed plus x plus 1 is equal to y. Y cubed plus y plus 1 is equal to x, right? How do you solve for y? Yeah, but you also have the plus y. If this plus y wouldn't be here, then sure, you move 1 to the other side and you take the cube root and you're all said and done. But the problem is you have y cubed and y. This is what I was saying. If it's a quadratic, then at least we have the quadratic formula that gives us the answer. But if it's a cubic or any other higher order, we don't know how to solve it. However, there you have an actual equation. You can put it in a calculator if you want, and it'll give you an answer. Okay? Yes?
How did we use our f prime of x at 3x squared plus 1?
Right here. Yeah, right here. Unfortunately, I wanted to do a problem because your problem is 36, which also involves a fifth order polynomial. So I wanted to do a polynomial problem, but unfortunately they're all zeros and ones, so it's kind of misleading. But here is where I put in 0 in that 0. I put it in for f prime, and I ended up with 1 because it's 3 times 0 plus 1. Well, 3 times 0 squared, I guess, plus 1.
Will we have to ever find to see if a cube is 1 to 1? Because it can't.
Well, in this instance, it's very hard to figure it out. So no, I mean, if it's not something that's a little easier to get a grasp on, then you're not going to be able to do it. Sorry? Yeah, I guess you could technically do that. I guess you could technically go to the second derivative and figure out if it's actually convex or concave. But actually, you actually don't need a second derivative. What you need is the first derivative. If it has a minimum or maximum, then it'll oscillate.
That minimum or maximum doesn't have another x2, right? If you find the minimum or maximum, then it doesn't have none of them have another.
The only way it would be 1 to 1 is if it doesn't have a minimum or a maximum.
Okay.
That's the only way, because then it actually has only an inflection point. Otherwise, it actually goes up and comes down, then it'll have a minimum and a maximum. And if you haven't taken calculus, you probably have no idea what we just talked about. That's basically chapter 4. As I said all along, we're trying to get these tools to actually be able to graph functions. So what we're going to end up doing is use the first and second derivative to actually get information about our function. First derivative is going to give us a lot of information about minimums and maximums, and second derivative is going to give us a lot of indication about the shape of the graph. But we'll get there, I guess, in about like 2 weeks or so. Okay. So moving on. Do you have any other questions? Logarithmic functions. The idea is the following. F of x is equal to, let's look at an example, 2 to the x. Okay? Graphically speaking, first of all, what is the domain of this function? We talked about it on Friday. Everything? What is the range? 0 to plus infinity, and it can't be 0, right? Everybody remembers this? Okay, now graphically speaking, this function looks like that, right? Where this point is 0 and 1. Well, it's clearly 1 to 1. Right? It's a strictly increasing function, which is 1 to 1. Everybody sees that? Well, this means it has an inverse. What is its inverse? We define f inverse of x to be log base 2 of x. Does this make any sense? Which means log base a of x is equal to y is equivalent to saying, do you remember how to do this, by the way? Back from pre-calculus? A to the y is equal to x. A to the y equals x. Right? Remember that? Yes? No? Don't care. Okay. So what do we know about f of x equals log base a of x? Can you tell me what the domain is and what is the range?
Domain is 0 to infinity. Range is all wheels.
Why?
Because I flipped the domain and range.
Exactly. The domain of an exponential function is all real numbers. The range is all positive numbers. So when you look at the inverse, then the domain becomes the range and the range becomes the domain. Do you remember that? It was written in the definition of the inverse, right? We said f had domain A and range B. F inverse had domain B and range A, right? Okay? Alright, laws of logarithms. And let's see if you remember any of these. Let's start off on a new page. First law says that log base a of x times y is equal to log base a of x plus log base a of y. Do you know why that's the case? Why?
It's always like that.
Why?
No, there's like these rules where you have something of x, y equals something of x plus something of y.
It's laws of exponents. That's why, because of laws of exponents. How about log base a of x over y?
Log of x minus y.
Log base a of x minus log base a of y. How about log base a of x to the n? N times log base a of x. Do you remember these at all or not really?
I don't remember those. Actually, yeah, I do. You bring it down. It's like the butterfly thing. Quite a strong word. Flying bird.
Okay, I'm going to give you the general formula that we're never, your textbook actually doesn't give you the general rule, but I will actually give you the general rule. Log base a of x is equal to log base b of x divided by log base b of a. This is called the change of base formula. Okay. Now your textbook only gives you this in terms of natural logarithms, but we haven't actually talked about natural logarithms. I guess now would be a good time to talk about them. So, do you have any questions about this?
Wait, is the last one going to be used a lot?
The key idea is the following. As soon as we're going to start talking about, so basically, what if I ask you, what is log base 3 of 4? And you're allowed to use a calculator.
Well, we have our A value, but how do we figure out what B is?
Well, this is for any b bigger than 0.
Oh, so B just stays like a variable.
So the key idea is you change the bases from base A to base B. Okay? Why is this helpful? How do you come up with log base 3 of 4? Well, you can take out your calculator. You're not going to find log base 3. However, what you were going to find is log base 10 and log base E. So this is the same thing as ln of 4 divided by ln of 3, where ln of x is log base E of x. The two most common logarithms are log base E of x, which is called ln of x. This is called a natural logarithm. And the other one that's actually very popular, especially if you're an engineer major, is log base 10 of x, which the standard notation for that is just log x. So for instance, if you look in your calculator, you will have these two logs. You'll have ln and you'll have log. Whenever you see log by itself without a basis, it is going to be a log base 10. Okay? Yes?
I forgot, what is the base next to the thing again? We just transfer it from exponential functions.
Yes. Now, let's look at some of these particular problems, because again, these logarithms, some of them might not necessarily be that obvious. First of all, let's see. Can you tell me if a is bigger than 1, what is the limit as x goes to infinity of log base a of x? Positive infinity. And what is the limit as x goes to 0 plus of log base a of x? I'll answer that for you, minus infinity. Why? Remember, log base a of x is equal to y if and only if a to the y is equal to x. Right? So picture-wise, if this is the graph of y equals a to the x, then this will be the graph of y equals log base a of x. Does that make sense? Yes? Again, one is an inverse of the other. We talked about the butterfly effect. If you look at this line, if you fold your paper on this line, you end up with the same line, right? Does that make sense? Right? So that means if I go to 0 plus, I'll go down to minus infinity. If I go to plus infinity, my graph will shoot up and I'll go to plus infinity. Does that make sense?
if it's just 0, it does not exist, right?
Well, no, because a to any power is never 0.
Oh,
Right? And so that basically tells you that log of 0 doesn't exist. Okay. Could you tell me what log base a of a is? 1. Right? Everybody sees that? Why? Because a to the first is a, right? Does that make sense? What is log base a of 1? 0, you say? Because a to the 0 is equal to 1.
oh yeah.
Right? Does that make sense? Okay. How about a to the log base a of x? X? Do you remember this? No? Why is this the case? Because a to the x and log base a of x are inverses of each other. Which means f composed with f inverse has to give you back x. Do you remember this? In the beginning of the class? So, not beginning, but about 15 minutes ago or so we talked about that. Remember this? Yes? So similarly, log base a of x, log base a of a to the x is equal to x again, right? Second one you can easily see also from the power property, right? The x can come in front and log base a of a is 1. But it's also because of the inverse properties. Okay. So let's look at some of these problems. First of all, I guess let me come back to inverse functions. So 23 on page 159. F of x is equal to e to x cubed. Can we figure out what f inverse of x is? So we start off with what? First step, y equals e to x cubed. Second step, x equals e to y cubed. Third step, how do we solve for y? This is equivalent to saying y cubed is equal to ln of x, which means y is the cube root of ln of x. Does that make any sense? Okay, so let's play with some of these problems over here. 43 on page 159. Part A. Log base 2 of 64. So we're supposed to find the exact value without a calculator. Well, even if you had a calculator, there's no log base 2 in it, right? Actually, I don't know. Does the TI-89 actually have different bases versus? Well, yeah. I mean, if you go to like a Maple or MATLAB or something, those for sure will have it. But so, what is that? It's a question, as in I'm expecting an answer. Do you know how to do this, or do you don't remember? This is the same thing as saying log base 2 of 2 to the 6th, which is 6 times log base 2 of 2, which is equal to 6. 64 is 8 times 8, right? 8 is 2 cubed. So you'll end up with 2 cubed times 2 cubed, so it's 2 to the 6th, yes.
It seems like it divides evenly, just by chance. The 64 will go down.
Well, that's the
Power of something.
That's the whole point. The whole point of this is to actually notice how you can use laws of logarithms to come up with the actual answer. How about part B? Log base 6 of 1 over 36. It will be log base 6 of 6 to the negative 2, which is negative 2. Okay? Or alternately, this is log base 6 of 1 minus log base 6 of 36. Log base 6 of 1 is 0, so you end up with minus log base 6 of 6 squared, which is equal to negative 2. Clearly you should get the same answer, but the point is you can look at it from two different angles. Does that make sense? Do you remember this stuff? Is it boring, or you just don't remember much of it? Okay, let's see. Use properties of exponents to expand the quantity. I always like these types of problems to some extent. So I'm going to make it a little bit different. So 47 star. If log base 2 of x is equal to 3, log base 2 of y is equal to 4, and log base 2 of z is equal to 5, what is log base 2 of x squared y divided by z squared? Bless you. 47 actually just said express this as a list of logs. So if I am to apply property number 2, I end up with log base 2 of x squared y minus log base 2 of z squared, right? And now if I apply the first property, I end up with log base 2 of x squared plus log base 2 of y minus log base 2 of z squared. And now if I apply the third property, I'll end up with 2 times log base 2 of x plus log base 2 of y minus 2 times log base 2 of z. So it'll be 2 times 3 plus 4 minus 2 times 5. Wow, I managed to choose some really nice numbers. It wasn't planned. Does this make any sense?
2 times 5 or 2.5?
2 times 5. It's 2 times log base 2 of z is equal to 5. Okay, 51. We're supposed to express as a one single logarithm. So 2 times ln of 4 minus ln of 2. Can we express this as a single logarithm? And as it turns out, we can do very much. Actually, it ends up being very nice, right? This is just ln of 4 squared minus ln of 2. So it's ln of 4 squared over 2. So it's ln of 8. Does this make sense? Okay. Well, let's look at something that's actually a little more interesting. 61. By the way, if you actually looked at your homework, I don't know if you actually saw how many problems you have to do for 3.2. The reason for that is I'm trying to actually give you the small amount, the least amount of problems I can, but because it involves so many different topics, I basically had to give you at least one or two from each topic. That's why they're so spread out. But that's why I tried not to say, from 2 to 72 or something like that, even, because then you'd really be working on them for a very long time. Okay, 61. 2 ln of x is equal to 1. Solve for x. So, in order to solve these types of problems, what you have to keep in mind is that e to the ln of x is equal to x, and ln of e to the x is again equal to x. Okay? So first things first, this is equivalent to saying ln of x squared is equal to 1. Which now, if I apply an exponential to both sides, I'm going to have e to the ln of x squared is equal to e to the first. Everybody sees this? Yeah? And now e to the ln of x squared is just x squared is equal to e, and so x is equal to plus or minus the square root of e, right? Because you're taking square roots. However, it can't be negative. Why can it not be negative? Because I started with ln of x. I can't put a negative number inside the ln. Okay? Let's see. How about 63? 2 to the x minus 5 is equal to 3. Again, the question is, what is x?
We log both sides.
So we apply ln both sides. So we're going to have ln of 2 to the x minus 5 is equal to ln of 3. Now what's the left hand side going to be? X minus 5 times ln of 2 is equal to ln of 3. So x minus 5 is ln of 3 divided by ln of 2, which means x is 5 plus ln of 3 divided by ln of 2. Does that make sense? Yeah? And you can't do anything about ln of 3 divided by ln of 2.
Log base.
You can write it as log base 2 of 3. But yeah, that's pretty much it. Okay, how about part B? Ln of x plus ln of x minus 1 is equal to 1. Again, the goal is to solve for x. So what do we do? The first thing we want to do is we want to combine the two ln's. keep in mind, you can't apply the exponential to both of them, because you have an addition. So the one thing that please be advised, I cannot say this is e to the ln of x plus e to the ln of x minus 1 equals e to the 1. Everybody understands why?
Why now?
Well, how can I say this? How can I apply an exponential to every single one of them? It's one thing if I apply it to the entire fraction. So there's a difference. What I can do is I can say e to the ln of x plus ln of x minus 1 is equal to e to the 1, the first. Do you understand this? It's on the same token as saying, let's say I have x plus 1 equals 5. If you square both sides, you can't say x squared plus 1 squared is equal to 5 squared. Right? Since this is not allowed, why would this be allowed? Whatever whatever operation you're doing on the entire left-hand side and not just individual terms. Is everybody understanding this now? Same thing is if you take the square root of both sides, if I have, again, x plus 1 is equal to 5, I can't go and say square root of x plus the square root of 1 is equal to square root of 5. Is that making sense? Again, you apply the square root to the entire term, right? Okay, now, since I guess I wrote it in orange here, we can do this. This is e to the ln of x. Laws of exponents tells us that this is the same thing as times e to the ln of x minus 1 is equal to e. Right? Does this make sense? Yes or no? Now what is e to the ln of x? X, you say? What is e to the ln of x minus 1? Times x minus 1 is equal to e. Now how do you solve for x? It must have been a very long time since you did pre-calculus. Since this was
4 or 5 months.
That's not a very long time.
I know.
So how do you solve for x, by the way? The quadratic formula. The only way you can solve for x. X squared minus x minus e is equal to 0. X is equal to 1 plus or minus the square root of 1 plus 4e divided by 2. So what is our answer? Just the plus. Why just the plus? Because the square root of 1 plus 4e is clearly bigger than 1. Right? Everybody understands why the square root of 1 plus e is bigger than 1? Square root of 1 is 1. Right? So if you add anything to 1, it'll be bigger than that. Right? So 1 minus the square root of 1 plus 4e is actually less than 0. And originally we started off with ln of x. Right? And so the only solution would be x equals 1 plus the square root of 1 plus 4e divided by 2. Okay? Technically, this is not correct. Or it is correct, but we avoid so the whole point is you have to figure out if ln of x makes sense. And you have to figure out if ln of x minus 1 makes sense. So technically I ignored the ln of x minus 1. We also should have to test to see that if this quantity is in fact bigger than 1. Because if it's not bigger than 1, then this doesn't make sense. Okay? But as it turns out, it is bigger than 1. Why? Because the quantity underneath the square root is bigger than 1. So 1 plus 1 over 2 would actually be 1, but because this is bigger, it'll be bigger than 1. Is that making sense? Yes? Okay, how about if we look at 65? How are we doing on time? I guess I have to hurry up. ln of x is bigger than minus 1. Solve for x. Well, no, technically, if you think about the graph, this is the graph of ln of x, right? Being bigger than minus 1 means I'm actually looking for all of these values, right? So, however, this is equivalent to saying x is bigger than e to the minus 1. And so x has to be bigger than 1 over e. Does that make sense? Okay. Last types of problems would be your favorite topic, limit as x goes to 2 minus of ln of 2 minus x. So what are we looking at? What happens when you put in 2 minus in for x? You end up with ln of 0 plus, which is minus infinity. Yes? I have a feeling you'll really enjoy this homework today and tomorrow. Considering, by the way, this is due on Wednesday. No, because it's 2 minus. So think about 2 minus as being 1.9. So you have 2 minus 1.9, so you end up with something a little bigger than 0. If this would have been 2 plus, then you just say it doesn't exist. Because you can't actually take it. Okay, how about, let's finish off things with a exclamation point. The limit as x goes to infinity of ln of 1 plus x squared minus ln of 1 plus x. So, any thoughts? If I am to put in infinity, ln of infinity minus ln of infinity, it'll be again one of those undetermined types, right? You have infinity minus infinity, and we don't know what to do. But using laws of logarithms, this is the same thing as the limit as x goes to infinity of the natural logarithm of 1 plus x squared divided by 1 plus x. So now if we take separately, what is the limit as x goes to infinity of 1 plus x squared divided by 1 plus x? Again, it is a question. I'm expecting an answer. It's just infinity. Why is it just infinity?
It's not going to infinity faster.
It's a polynomial over a polynomial, and we talked about that as being, you look at the power, the largest power. So that means that this is just going to be plus infinity, because ln of infinity is infinity. Right? Does that make sense? Okay. Alright, so we'll stop here, and Next time we'll actually find out what the derivative of all of these lovely functions are.